Alright, now we'll do our last right-hand rule number 3. If a charged particle moves through a magnetic field, it feels a force and will move in that direction of the force. So point your arm in the direction of the velocity of the charged particle, your fingers curled in the direction of the magnetic field lines, and your thumb points in the direction of the force. So for positive charged particles in the figure below, it is force upwards according to the right-hand rule number 3. Now, for negative charged particles, it's force in the opposite direction as the positive particle. One way to remember the direction for a negative charged particle is to use the left-hand rule instead, or just use your left hand instead. Now remember, electrons are negative charged particles, so read the questions carefully. In this equation, F stands for the magnetic force, Q stands for the amount of charge, V stands for the velocity of the charged particle, and B stands for the magnetic field. And theta is the angle between velocity and magnetic field lines. So in this example, a negative charge, negative Q, is placed at rest near a magnet. Will the charge begin to move? Will it feel a force? What if the charge were positive Q? No, it will not move whether it's negative or positive. Therefore, also does not feel a force. A charge at rest has zero velocity. Magnetic fields only exert force on moving charged particles. In this example, we have a magnetic field exerts a force of 8 times 10 to the negative 14 newtons towards the west on a proton moving vertically upward, or I'm going to say out of the page, at a speed of 5 times 10 to the 6 meters per second. When moving horizontally in a northerly direction, I'm going to say up, the force on the proton is 0. We want to determine the magnitude and direction of the magnetic field in this region. We'll start off with our new equation. We'll rearrange the equation to solve for the magnetic field and plug and chug to get 0.10 Tesla. Now, typically, for the direction pointing upward, or more commonly I'm going to say out of the page, a common symbol used is a circle and dot in the middle, or just a dot. If it were pointing into the page, or anything pointing into the page, the symbol will be used as a circle and X in the middle of the circle instead of a dot, or it will just be just an X. One way to remember the dot or X is think of a bow and arrow. An arrow coming out of the page or towards you, you'll just see a dot. And an arrow moving into the page or away from you, you'll see the feathers like an X. So for the direction, point your arm upward into the air, point your thumb to the left, and your fingers should curl in a northerly direction. The statement, when moving horizontally in a northerly direction, the force on the proton is 0 makes sense because mathematically theta would be 0. Thus, the force on the particle would be 0. Here's a good visual picture showing a charged particle circling magnetic field lines. In this case, the charged particle is an electron. At point P, point your left arm to the right, your fingers curl into the page, and your thumb points downward, or to the south, I guess. So as the electron moves to the right, it is forced downward towards point Q. And then repeat this process at point Q, and you'll see that the electron continues along the circular path. We can actually find the radius of the charged particle in a circular motion. So here, if we have an electron that travels 1.5 times 10 to the 7th meters per second, and it's placed in a plane perpendicular to a uniform 0.01 Tesla magnetic field, It says describe its path quantitatively, meaning just find the radius. This time we'll start with some of the forces, and since the particle is moving in circles, sum of the forces equals MAC. The force in the particle is a magnetic force, so we'll plug in the magnetic force equation on a charged particle, and also make the substitution in for centripetal acceleration. You can see that velocity will cancel out there, so the equation reduces down a bit. Now we can rearrange the equation to solve for the radius. From there, it's just a plug and chug. The mass of the electron, the charge of the electron, its speed, and the external magnetic field it's moving through to get a radius of 0.0085 meters, or I can just say 0.85 millimeters. Here's a table summary of all three right-hand rules we've done so far in this chapter. The last equation we'll discuss in this chapter is finding the magnetic field strength next to a wire. As you know, current flows through a wire and creates a magnetic field around the wire in closed loops. The closer you are to the wire, the stronger the magnetic field is. B stands for the magnetic field strength. Mu naught is a constant called permeability of free space. It means how easily can a magnetic field form in a vacuum or air. And we'll use the value below, 4 pi times 10 to the negative 7th. I stands for current, and R is a perpendicular distance away from the wire. In this example, we have an electric wire and a wall of a building carrying a DC current of 25 amps vertically upward. What does the magnetic field do to this current at point P, which is 10 centimeters due north of the wire? It looks like it's east. We'll use our new equation, and from there it's just a straight plug and chug to get the magnetic field strength at point P to be 5 times 10 to the negative 5 Tesla. And if you use the right-hand rule number 1, thumb pointing in the direction of the current, your fingers curl in the direction of the magnetic field, at point P, the magnetic field lines are pointing into the page. In this example, we have two parallel wires 10 centimeters apart, carrying a current in the opposite direction. I1 is 5 amps and it's out of the page, and I2 is 7 amps pointing into the page. We want to determine the magnitude and direction of the magnetic field halfway between these two wires. Now, since we have two wires, we'll apply the magnetic field equation twice. Plug and chug to get both values of the magnetic field strength in the middle. From there, you have two options. Either add or subtract these two values to determine the net magnetic field in the middle. To decide, use the right-hand rule number 1 to determine the direction of both magnetic field lines in the middle. In this example, we have both magnetic field lines that are pointing up, because for I1, pointing out of the page, magnetic field lines is represented by blue, which is your fingers curling around. And right at the middle, B1 points up, and then for I2, again, your thumb's going to point into the page, fingers represent the direction of magnetic field lines curling around, and right in the middle, at B2, it's also pointing up. So therefore, we will add these two values together to get 4.8 times 10 to the negative 5 Tesla.